Hello, everyone. I'd like to welcome you today to the Critical Materials Innovation Hub webinar series that has been designed for CMI and by CMI. I'm Cynthia Howell, and I'm the Education Workforce Development Manager at Colorado School of Mines for CMI. And today I'll be your moderator. I'd like to tell you a little bit about the webinar. And if you come up to the next slide here. The CMI webinars are hosted by Colorado School of Mines, and if you have any suggestions for a future webinar, please don't hesitate to put it on the survey or email us. Again, this is designed for you and by you, ultimately. This is a public webinar, and a recording is going to be available next week at aimslab.gov/CMI. Under the webinar menu, also know that we have a YouTube channel, Critical Materials Innovation Hub, and please subscribe there so you'll also get updates. We are going to hold the Q&A till the end of the session, the end of the presentation. But please, as you have a question, please get it into the Q&A box so that we have questions queued up when we get to the question and answer session. I'd like to take some time today to introduce our presenters. Professor Ian Lange is a professor at Colorado School of Mines and chairs the U.S. Commodity Futures Trading Commission's Subcommittee on Metals Markets in Transitional Energy. He's also a member of the Colorado Governor's Revenue Estimating Advisory Committee and served as senior economist for energy at the Council of Economic Advisors under both Trump and Biden administrations. And he's going to be joined today by colleague Scott Thomsett. He has 18 years of experience in the mining and minerals industry. He is currently serving as CEO of Roviok, a minerals intelligence firm. And he has experience across multiple jurisdictions globally, having previously worked for PwC, First Quantum Minerals, Bolivian, Northvolt, and in roles of finance, strategy, and M&A, and critical mineral sourcing. And I really don't want to take any more time out of our presenters' time. So Ian, if you wouldn't mind taking over here.
Thank you, Cynthia. Yeah, excited to be here. So it's just some background materials to start. So to keep everyone sort of level set, right? So gallium and other byproduct metals that we are generally now calling critical minerals used to be called minor metals. They were generally called minor metals because they were produced as a byproduct of some sort of major metal. So as you dig a major metal, say nickel, bauxite, copper out of the ground, there will be these other minerals that come along for the ride. I am no geologist myself, but my geology friends tells me, like, if you look at the periodic table and you go up and down, those are the things that are generally found together. So for example, if you're interested in something like cobalt, right, generally mining companies in the past have not been, and it's changing a little bit now, but they have not been looking for cobalt specifically, they're looking for copper. And as they dig out copper, cobalt is coming out of the ground. And so generally what has to happen for many of these critical minerals that we're interested in is you either separate them before you make a concentrate. So for example, in something like antimony, you need to pull that apart from the gold before you send the gold to be processed. For something like gallium, right, you'll make either a bauxite or a zinc concentrate, and then it will be generally separated at the processing facility if that facility has a separations unit. And so I would say the important thing to think about or to know if we want to have intelligent discussions about minerals like gallium and antimony is that if you do not separate these out somewhere, they basically just go into the trash or tailings pond, right? So we'll say essentially all gold mines in the US today will pull antimony out of the ground with its gold. They'll separate the gold away from the antimony and everything else, and they'll throw that part away and then take the gold on to be turned into the gold bars, you know, that they can sell or that we see in films and things like that. Some research here at the Colorado School of Mines basically estimates that the amount of many of these minerals that we actually pull out of the ground and then throw away is equal to or above how much we consume in the United States. So many of these critical minerals, right, we have around, we actually already do mine them, but we don't bring something available for sale. Because we just sort of put it off to the side and essentially throw it out. Oops, sorry. The way I tend to think about some of these issues is that a lot of the investments, like getting gallium, getting germanium, getting antimony, is kind of like a nickel or a dime sitting on the ground. I generally think of it more as like a nickel, but I was afraid we might get confused with the mineral nickel. But imagine you're walking by and you see a dime sitting on the ground, right? You say, I could pick that up, right? It's not like it's not profitable. It's not like by bending down to pick it up, a dollar bill falls out of your pocket, right? So this isn't like a net negative profit to say, pick up this dime, or in some case, separate out, say, your antimony, but it does require some work. And so what has happened in the United States over the last 20 years is that firms have kind of said, I'd rather pick up a $10 bill. I'm not interested in this dime that's sitting on the ground. And as a result, our ability, whether that be technically or what's available to us in order to separate out these byproducts and put them into the supply stream has sort of gone away. And so from my standpoint, is if you're a policymaker, if you're thinking about policy, is right, we have these nickels sitting on the ground. How do we encourage firms to bend down and pick them up? That's kind of the main question that I see when I'm talking to policymakers. And in case you're wondering, can some of these investments have big impacts? Here is some work that we have been doing in our project for CMI related to relatively small investments that firms have said they could make. Most of these are coming from public information that's available on a firm's webpage on how that investment that they could make would alter the supply risk. So if you look at the graph on the left, what you have is the 45-degree line will show you what would happen if basically there was no investment made, or an investment in some byproduct recovery had sort of no impact on the supply risk. As you move away from that 45-degree line, what you're finding is that there is a change in how the supply risk to the United States evolves if we were to make that investment. So for example, for germanium and gallium, our research indicates that if a zinc refinery in Tennessee were to make the investments that they claim they can make, right, we would lower the supply risk from something around a 75-80 to about a 5 on the supply risk category, which would essentially render these things not critical according to the definitions that are used of criticality. And there's a couple other examples here. Some of them have a bigger bang for the buck, some of them have smaller. We are obviously particularly impressed with like the tellurium separation circuit at Rio's Kennecott facility, which was incredibly cheap, relatively, to have a decent sized impact on supply risk. Now, one of the things that I would think about as an economist is when you make some of these small investments, you end up altering the market size by a large amount. So we can think about things that in our daily life, like we made here about OPEC decision-making around cutting some oil supply or something like that. Those are usually cuts of like, 0.5%, 1% of total market supply. But if you make an investment to bring a mineral like gallium or a mineral like antimony onto the market, these are extremely small markets to begin with. So you can have large increases in total world supply. And of course, large increases in total world supply will depress the price of the product unless you have sort of some policy in mind that will also uptick in the demand for that product. And so what is the mechanism that would encourage a firm to make an investment in a product when they know that that investment will crash the price of the product they're trying to sell? This is a ongoing piece of research that our CMI project is thinking of, is what is this mechanism that encourages firms or that helps firms make investments in these products when that investment will have a large change in the price that they expect to receive for the product. I think with that, I'm going to turn it over to the person you're probably really here to see, the person who knows a lot more about this topic than I do. And I'll pass it over to Scott to tell you a little bit about his thoughts about these markets.
Thanks, Ian. Hi, everybody. A little bit on Roviok. So we're a European-based minerals intelligence firm. We work with mining and metals companies globally. We're also currently doing work with DARPA on their critical minerals related program, Open Price Exploration for National Security. Jump to the next slide, Ian. I'm hopefully not going to take too long to give enough time for questions. So here's an outline of what I'll cover. So firstly, an overview of the value chain for gallium, quick primer on the market aspects, some mapping on where the feedstock of gallium is currently coming from, and then I'll present some modeling on the competitiveness of potential new supply outside of China. And next slide, thanks, Ian. So this is the gallium value chain, so where it comes from and where it ends up on the right. So primarily the byproduct of alumina refining and a small portion from zinc smelting to produce primary low purity gallium. It then changes hands to be converted to higher purity, and then it goes into either the semiconductor value chain, ending up in or on wafers, which end up in many different devices, including LEDs, integrated circuits, power electronics. And then another large portion in China ends up in their solar industry, although that share is declining. And then in magnets for EVs and wind turbines, etc. And as I'll show in a moment, the gallium market from a volume perspective is tiny, but it has a far-reaching impact in terms of where it ends up in the industries it ends up in. So quick primer on the gallium market. So don't take these figures as definitive, but rather indicative and to highlight the nature of the problem in these type of minor byproduct mineral markets dominated by one producing country. So the chart on the left shows the supply and demand fundamentals as of 2024, and then how it could potentially look at the end of the decade. So primary supply is almost all in China today, sitting at about 760 tons of gallium. Secondary supply tops that up, and something to note on secondary supply is that it's almost all from new scrap from the semiconductor wafer manufacturing process. So the green line shows the demand, the yellow line shows the capacity. And as you can see, China has significant additional built capacity today. So they're operating at about 80% of that. And they've got new capacity able to come online over the next couple of years. Additionally, there are several new projects announced outside of China which have the potential to come online by the end of the decade. We're also seeing significant inventory build-up in China, as their demand in 2024 was actually about 630 tons, but apparent consumption was around 720 tons. Chart in the middle shows the pricing of gallium. So since the export controls put in place by China, we can see significant bifurcation in the prices for gallium. So the average difference between the Chinese price and the Rotterdam price before the export controls, i.e. the average of 2022, was only about 14% difference. However, as of last month, that difference is now 180%, owing to the fact that there is no meaningful primary sources of gallium outside of China today. Finally, the donut chart on the right is showing the split of the demand in 2030 by the different end users. So with the largest shares being LED, magnet, and integrated circuit markets. We see the photovoltaic share of the market declining in relative terms, as that's driven by China, where they're using less gallium as they shift to technologies in that solar sector. Long story short, there's significant demand growth, but there is potentially significant oversupply in the market in a non-bifurcated market situation. As I mentioned earlier, so gallium refining is usually a byproduct of alumina refining and in a minor way from zinc smelting. So to understand the origin of gallium production today in an extractive context, so the source of the ore, we've mapped the feedstock with the relevant alumina refineries and the zinc smelters, which gallium refining is attached to. So for alumina, we've traced back to the source bauxite, and for the zinc smelting, the source of the zinc concentrates. Within China, much of the bauxite was previously sourced domestically and it had quite high gallium concentrations. Now, much of that is being supplemented with imported bauxite as that alumina refining capacity is scaled beyond their domestic supply. So that imported ore is now primarily coming from Guinea, which has lower concentrations of gallium, and that's having an impact on their cost to produce gallium, which I'll talk about later. On the zinc side, this is relevant for Japan and South Korea. Much of their zinc concentrate is coming from Australia and Central America. And then here we're showing the next step in the gallium value chain where we go from primary or crude gallium production, which is about 4N gallium, to high purity refining, which is then sold primarily into the semiconductor value chain. So that's where we start to see a bit more diversity outside of China. So how is gallium primarily produced? So here's a breakdown of how gallium is typically produced in China. This is by far the most efficient method industrialized. So in simple terms, it's an ion exchange process. They use a bleed stream of the bioliquor from the host alumina refinery and then return that bioliquor back to the refinery. It's not necessarily unique metallurgy and it doesn't require significant expertise in a relative sense. In the process, the bioliquor passes through a resin that grabs the gallium ions. Sulfuric acid then strips the gallium off the resin, and a base, being caustic soda, cleans the resin for reuse. The stripped gallium is then precipitated, and then finally that gallium precipitate is then purified through electrowinning, where an electric current then extracts the gallium metal. Doesn't necessarily require much specialized or costly equipment, and it's cost effective in China because of the existing alumina refining capacity and also the metallurgical ecosystem overall, low power cost, and then their ability to source reagents cheaply, in particular the resin. In an operative sense, so the resin is actually a chelating resin, and the most recent export controls announced by China in the beginning of this year, they actually also restricted any technologies related to the refining of gallium, and that means that that particular resin, and China dominates the production of that also. So given a scenario in the future where the current export controls no longer exist, i.e. we don't have a bifurcated market we have today, and the market is therefore fundamentally oversupplied, new capacity needs to be cost competitive with the dominant market player being China. So we've modeled some scenarios showing where and how new capacity could theoretically be cost competitive to China. So taking all the traceability data that we showed earlier, so we look at some representative alumina refineries in different places around the world where it could make sense to add a gallium side stream. We then apply a techno-economic model to see under localized conditions as well as the operating characteristics of each alumina refinery, how cost competitive it would be compared to a representative Chinese benchmark. This also accounts for a theoretical gallium potential in the bioliquor per refinery to scale each operation. So what I'm presenting here is the cost to operate on a US dollar per kilogram of gallium production. So what the results show us is that with a more modern flow sheet, production could be relatively on par with the Chinese in several locations, and in particular in Australia, it could outperform under modeled conditions. That's helped by favorable operating conditions of the Australian alumina refineries and comparable reagent costs in that region, but also driven by favorable bioliquor that presents considerable gallium potential as a consequence of the high gallium concentration in the bauxite feedstock from those areas. And then at those volumes, of course, however, this would essentially flood the market in a non-bifurcated world, as Ian pointed out. So to do this economically in the long run, it requires offtakes that pay for that supply chain security above the cost to produce for these type of refineries to remain profitable. Next slide. So finally, I want to show the theoretical impact of having higher gallium concentrations in the bauxite feed. So here's the model flex for different scenarios of increasing gallium ppm in that origin bauxite. So there's a meaningful cost benefit for every 10 ppm increase in the gallium in the bauxite. That said, the bauxite needs to be overall favorable to the host alumina refinery in general, so not just gallium alone. And given the difference in between potential earnings from gallium versus the alumina production, it's hard to see an alumina producer favoring gallium production at the expense of alumina. So over the last few months, we're seeing this concept being validated with several reports out of China noting that gallium producers are seeing their costs increase considerably as a consequence of a greater proportion of imported bauxite ore with low gallium concentrations being utilized in the relevant alumina refineries. And that's all I've got to show for today. So thanks for your time, and then happy to return back to Ian to close it out.
Yes, thank you, Scott. Yeah, and so please keep the questions coming in. So just to wrap up, we wanted to talk about some takeaways, right? So many of the minerals that CMI works on are byproducts of larger metal markets. Those investments can be or have been overlooked, generally due to their small value and their potential impact on the markets on which those would sell through. However, that does not mean that there aren't good options, right? So, for example, as Scott laid out, there are a number of good options outside of China for gallium production, mainly focused in Australia. And some of that can be taken advantage of, sort of if, as Scott mentioned, maybe a bifurcated market, so you're not competing with the Chinese, or if there are other ways to encourage investment in OECD or Western countries. With that, we'll open it up to the questions that are coming in through the Q&A. If you did want to talk more gallium after, or any other metals after this event, here are our contact informations. And so right now, I'm going to start just with a couple of the questions that have come in. The first one I think I'll say is for you, Scott. The first question was, what kind of resin is used in the ion exchange?
Yeah, so it's a chelating resin. So within China, they use an amidoxine resin, and then the equivalent outside of China is generally Calex 100, which is essentially hydroxyquinoline, which is then bonded to PVC beads, which looks like a kind of, pale caviar. And that's something that, to essentially support an ex-China supply chain, getting the cost of that resin down would greatly benefit the overall cost curve for ex-China production.
Thank you, Scott. The second question that's coming here is, so people have been very impressed by your techno-economic analysis of the bauxite refining or alumina refining. And so they're wondering if you've done a similar study on zinc, on the zinc side, so the gallium possibilities from zinc smelting.
Yeah. So we have on zinc, and we've also done that for germanium, where germanium is primarily produced from from zinc smelting. So, but what we see on the zinc side for gallium, it makes up a much smaller share of the current production, and it's also quite higher cost than doing it from alumina refining.
Perfect. And I'm sure, like I said, Scott's emails here. I'm sure if he'd happily do more modeling or share more modeling if someone wanted. Right. There was a question here on your analysis of the costs of providing some gallium to the market. One person noticed that the labor costs in Canada were smaller than the labor costs in the United States from that chart. And I don't know, maybe if it'd be useful, I can go back to that slide, Scott. But they were just wondering, why is Canadian labor costs smaller than US labor costs? If you have that information off the top of your head.
Yeah, it's eagle eye, Scott. So we see the labor costs being relatively fixed. So it essentially scales as the gallium, the size of the gallium production increases as well. So, we see as essentially economies of scale on that side of things. But I'll have to double check the numbers. I think that we might also have lower labor rates in Canada in that sector as well.
Thank you, Scott. This next one I'm at least going to start with, and then I'll pass it over to you, Scott. So this question is, do we see a shift in the future where gallium is no longer critical because of the way technology has evolved? And like I said, I'm gonna at least throw in one thought here, and then I'll turn it over to you, Scott. But so at the Colorado School of Mines, we do have a space resources program. We very much like to say it's the only space resources program, although obviously the more words you put in there, the less likely someone else is going to have those exact same words. But nevertheless, the space resource program has allowed me to learn a lot about, say, like the satellite industry, and there is use of gallium, as I believe it inhibits the sun's rays from really degrading some of the pieces on the satellites. And so I believe that it's probably more likely to see more gallium used as the space sector becomes a bigger thing or bigger part of, say, Western world's GDP, or just the world's GDP, as we do more things in outer space. I would say that technology shift would be gallium intensive and use more gallium. But I'll turn it over to you, Scott. Do you have any thoughts about a technology shift away from gallium, possibly?
We don't, for its particular uses, other than what we're seeing in the solar sector, where they're shifting from P-type to N-type, where you get, essentially kind of substitution for gallium. That's not true substitution. Other than that, yeah, we see significant growth from the demand side for these more high-tech uses, like you mentioned. And actually, if you look at the demand curve under different scenarios beyond 2030, that's where we really start to see an uptick in the growth because of the adoption of some of these technologies. And also, we're seeing an emergence of the gallium nitride as a semiconductor, particularly for power electronics, being more widely adopted before the end of the decade. And then we start to see that having a considerable impact after 2030. But in terms of, do we see a future where gallium is no longer critical because of a technology shift? I think, as we see with the supply side, we can very quickly see that adding new capacity is not a significant investment. And so when that new capacity comes online in a more diverse way, then we'd see that criticality drop very quickly.
Yeah, right. So on the supply side, we could have changes in criticality because we change the supply risk. But on the technology shift side, which I think is maybe more on economic importance, say the y-axis of a criticality measure, there's harder to see something that makes that much less critical. Although I must say I do appreciate that question, because it allows me the opportunity to also always talk about europium, which is one of my favorite examples, at least, of in the 2012 DOE critical minerals assessment, that was one of the most critical. And of course, by now it's not even listed because it was used in CFL light bulbs. And of course, we have new technologies of LED light bulbs, and europium is not used in the same way that we expected it to be. So it's a great example of we are kind of looking at now, and we have guesses of the future, but it's really hard to predict the future. So great question there. Next question, Scott, this will be up your alley. Let's see if I can say this correctly. What electrode material is used for the electrowinning step of the process?
Sorry, something where I'm probably out of my depth on that one, so
I'm definitely out of my depth.
I'll pass on that one, yeah, but it should be pretty standard.
Yes, we'll have to find a metallurgist to help us out with that one. Right. Okay, so we have a question that's wondering, you showed obviously a number related to the cost of gallium. And so the question was, that number is higher than traditional prices for gallium. And so I guess they're wondering what kind of risk is put into those numbers.
Yeah, I mean, so that's what we're seeing as the true cost as of, say, 2023, 2024. So if you backcast the model, accounting for the price differences and everything, you'll certainly see that cost being lower, but we're seeing that as being the true floor price in China as well. Taking note that within there is the cash cost to produce plus representation of depreciation, just to account for the relative capex amount as well. So with anything, if to use these numbers, it depends on the context and depends on the time horizon and those type of things. So just feel free to reach out, and the models can be flexed for whatever scenario.
Yes, and definitely, right. All of these things are based on models that have assumptions in them. And so, it's clearly, I know one of the things that's come up recently in my conversations, right, is so for example, initially Narstar gave a number of around, say, like 150 million for the separations unit in Clarksville to pull the germanium and gallium off its zinc refining. And if you talk to them more recently, they'll say the number's 300. And so why the number doubled is kind of unknown. But again, all of these things are varying over time. And presumably, as the price of the product you're interested in goes up and everybody knows what you're doing, they're going to raise the price of the input costs to you, right? So if everyone knows that the output price is doubled, they're not going to sell you your inputs at the same price they sold it to you before, let you take that doubling as profit. Again, humans are pretty innovative kind of animals, we'll say. There was a question in here specifically about the Sheep Creek deposit. I'm not sure if you have any specific information about whether that would be useful to altering the US's cost number.
Yeah, that side of things is interesting. So as we've seen the gallium prices outside of China spike, and also there being quite a lot of interest in gallium and some of these other minor metals, we're seeing them start to bubble to the surface in resource statements and exploration and drill results. So previously, companies wouldn't have even bothered to sample for them. Now they're being reported. I think the real question is then the downstream step, right? So as Ian pointed out, like a lot of these things are left in the waste streams, and it's not always economic to then process them. So I think with Sheep's Creek, it comes down to, where could that material actually then go to then extract the gallium. So yeah, something to look at, but I wouldn't see it having changing the supply situation on its own.
Right. Yeah, and you make a good point that all of these things are, we'll say, elements or minerals that we know are in the dirt. In many firms, don't when they go for their assay, like say in their feasibility study, don't select for them or don't look to see what's there, because again, it's not what the investors are looking for. One of my favorite stories, talking to a colleague of mine who spent a number of years at Newmont, and obviously when antimony kind of became a thing through potential Chinese export restrictions and things like that, I asked him, hey, if you were in corporate development at Newmont, did you guys ever think about antimony? And he said, I think you're making up a word. No one in Newmont's corporate development ever heard of that word. And you're like, what? Like it's bound with gold. It must be. But again, from a business perspective, if it's not what investors are interested in, if it's not, what you think is going to drive profitability of a project, you kind of just, swish it aside. So next question is, do any of the American or Australian firms handle refining in China? Or do the Chinese do all the refining at those alumina smelters to get the gallium? My apologies.
My knowledge, it's all Chinese owned. Yeah.
Okay. So potentially getting some of that information, if there's any trade secrets or technical know-how that we don't have, it could be, we'll say, difficult to catch up.
Yeah.
Which is something CMI is trying to fix itself, and something, folk here at CMI probably know a lot better. So
yeah, and I think, as I pointed out, I think the metallurgy though is known. I mean, gallium production did happen outside of China in a more meaningful way up to about 2016. It was more the market conditions with the ramp up of the capacity in China that rendered those projects then unprofitable. They were previously, a lot of them were using a solvent extraction flow sheet, which was then higher cost as well. But if they were to restart today with a flow sheet that's similar to what the Chinese are using, then under those conditions, then it could potentially be cost competitive.
Perfect. Thank you, Scott. Okay, so the next question again is a chemistry one. I'm hoping you can help me here. Let's see, I get the baler is liquor that is highly caustic. Can the caustic from the baler be used in the synthesis of gallium?
So yeah, I mean the bioliquor as a bleed stream then flows through, but they add fresh caustic soda in the process as well, but they generally take that, just the same caustic soda that they're using in the alumina refining process, in the gallium refining step as well.
Perfect. Much better than I could have answered that. Okay. There is a question about the microbes or bacteria that are becoming, we'll say, more common in the startup / investment scene, at least here in the United States. So do you have any thoughts about using microbes or bacteria in the refining of some of these things? How might their efficiency or cost compare to traditional methods? So not something I don't have a good sense on. Maybe you have some, Scott.
Yeah, not in particular on microbes or bacteria, but in general, I have seen some potential flow sheets that are at a meaningful TRL level that on paper are quite compelling in terms of cost competitiveness, both on the OPEX side and the CapEx side. So any breakthroughs in that area can then obviously shift the whole cost curve significantly. So yeah, there's always room for innovation for sure.
Perfect. Yeah. So this next one's for me. How do you define supply risk in a criticality assessment? Like a minor metal to a larger commodity, the supply risk may have maybe due to swings in the market prices of a larger commodity. And so to the question specifically, right? So generally, in criticality assessment, supply risk, has some measure of a diversity index, like a Herfman-Herfindahl index. What countries are you importing from? How risky are the countries that you're importing from? Clearly, something that you're consuming yourself is sort of, we'll say, weighted very highly in terms of like, then you don't have a lot of supply risk. So if you were producing, 50, 60, 70% of your demand yourself, the supply risk is gonna inherently be relatively low, because you presume you won't fight yourself, you'll get the material from yourself. But like I said, it's generally, think of some combination of like a diversity index, like a Hirschman-Herfindahl index, and some weighting for how risky the folk you do import from it are. And so, you can definitely cheat a little bit with the method, because let's imagine we were to start producing some of these materials ourselves. We can just assume, if we assume we are going to then stop importing from the riskiest country possible, that would have the biggest change in a supply risk. Where if we assumed that the increased domestic production wouldn't offset imports from relatively non-risky sources, then that would have a smaller impact on supply risk. But yeah, they're generally, just think of them as like diversity indexes. The more diverse your potential country mix of imports, the smaller the supply risk. It's not perfect. It's kind of what we have right now. I know at least one thing's me personally, right? Countries don't tend to make, production/investment decisions. Companies do. And so by having this data by country, you're missing out on the decision maker, in that supply risk, because again, it's not like Australia decides what's mined. It's the companies in Australia that can decide this is no longer profitable. I don't want to do this. And so there's a bit of a just wiggle room you have to deal with, because the data is not good enough to be able to know by country, by firm in some sense. So we have a question here. You have basically, like, you showed a data set, Scott, that had every 10 parts per million increase in the concentration of gallium and how that impacts the economics. Have you gone much lower than the numbers that you've shown there? Or, is it linear? Is it exponent? I presume at some point it exponents into the cost if you get close to zero, but.
So what we're seeing in a practical sense, I think what I've heard in the industry is that the cutoff would be around 20 to 30 ppm before it, in your average bauxite feed of an alumina refinery, before it just doesn't make sense to then extract the gallium. The challenge is actually, like, in the bioliquor, the gallium reaches an equilibrium. So that can actually remain quite stable, but then it's in proportion to the bioliquor. But yeah, I think it's around 20 to 30 ppm.
Okay. Okay.
Yep.
And then the last question that we have here, or that's been submitted already, is does the U.S. have a plan to secure its gallium needs in the near future? And I've always found, at least from where I sit, let's just say, I don't want to say industry is probably the wrong word, but every industry I go into, I hear a story of like, well, you know what the problem is? We just don't have a plan for this. And so, I mean, I think just in the current either political environment or in what you might call like in a democracy like the United States, it's really hard to have a long-term plan, right? Because leaders change, thought processes change, markets change, and all of that. So I guess if we use the term plan very broadly, I mean, I would say, yeah, like there's, for the last, maybe 10 years, 8 years, there's been a lot of interest in sort of critical minerals policy, or what policies can be done around critical minerals. And I would say, from the Obama administration, there was a lot of, we'll say, hands-off industrial policy, a lot of more, just basic R&D, and we'll hope that some of that R&D gets is useful in other places. Sort of since then, we've kind of seen increasing, specific industrial policy, whether that be things like the domestic content requirements through Inflation Reduction Act subsidies, to the more recent executive order from the Trump administration to really streamline permitting reform and push forward permitting of new projects. I believe there was something about building refineries or smelting facilities, on federal lands, making it easier to go into the tailings. So I guess I would call that a plan, right? But the plan of the current administration seems to be along the lines of just get things going through, improved permitting, we'll say expectations. Obviously, Congress might still have to act. We'll see what happens if Congress alters the Inflation Reduction Act or bipartisan infrastructure law provisions, and how that would alter things. But currently, through, say, like the executive orders that we see, it seems to be focusing a lot on, we'll say, permitting, and there is not a lot of subsidies being handed out just yet. Again, partially because it's Congress that is the power of the purse and not the executive branch. But I've talked a lot. I guess, Scott, I'll let you, at least, if you have any thoughts maybe about what you've seen in Europe through the Critical Raw Materials Act, or in Australia, are there plans around gallium or some of these other critical minerals that either differ significantly or are useful to for audience to know about?
Yeah, no, there are certainly plans and I believe work going on outside of China on scaling up, studying and scaling up specific production for gallium. There is the most recent within Europe was in Germany. That would have the potential to restart. In Greece, they've also announced, potentially bringing online gallium capacity with the facility there. But then, flipping that in terms of what should a plan also account for. So, as we pointed out, the byproduct minor metal market nature of something like gallium, when you do bring that supply online, and if we get a situation where the export controls from China are removed and we have a non-bifurcated market, then we have an oversupplied market for a period of time as well. So then it's, what support is needed for these facilities to continue running and not at a loss, right? And the value add on gallium is quite significant once you get to the final end products they end up in, particularly in the high tech sector. So what is needed is, like I mentioned earlier, offtakes that pay essentially that insurance premium for that security of supply. Or things can look like, price floor support mechanisms, national stockpiling to ride out the volatility in the markets. No single method is necessarily perfect, and everything is challenging and doesn't sometimes always make perfect, free market economic sense. But when you're accounting for security of supply, then you need to have these mechanisms in place to support these type of, what we'd call like emerging mineral markets.
Yeah, I remember, at least in economics, right, there's this idea of something called Say's law, and Say was I believe a French economist. But anyways, the idea was that supply creates its own demand. But sometimes the timing is a little bit off. And so if we bring some supply of gallium to the market, then perhaps something like a stockpile is a way to ensure that supply doesn't fall back off while demand starts ramping up. And so, as I mentioned, like say the space industry might be a place where we see expanded demand for gallium, but they might not be able to have their production plans in order as fast as the gallium can come to market. And so one could think about ways to smooth that transition from the supply leading to the demand. And I guess I'll turn it over to Cynthia. I've seen you come off of mute a couple times. My apologies for
No
continuing to talk.
worries. I really just wanted to make sure that that there was time left to thank you, both Scott and Ian, for such an excellent presentation on gallium. You told a very thorough story. You painted a picture for us where we can see where it's found in the world, kind of what the markets are like, the challenges of separation, and most importantly, as you've presented this to our CMI audience, the room for innovation. And obviously that's what CMI is all about. So who knows what else can be developed just as a result of hearing this whole picture about gallium. I'd like to thank our audience for being here today. And I want to remind you that this recording is going to be available next week at aimslab.gov/CMI and also on the Critical Materials Innovation Hub YouTube channel. Next webinar will be on June 17th when Adam Johnson, the CEO of Principal Mineral, will represent navigating volatility in critical material markets. Obviously, you can find all of that information in Critical Times as we do monthly and also on the website. If you have a suggestion again for a future webinar that will suit you as the CMI audience here, please don't hesitate to get that information to us. Again, extra thanks to Scott and Ian for such an excellent presentation, and we look forward to seeing everybody next month.